Alright, another DraftScience video presentation. Put the keyboard away. Just to reiterate, I basically live in a shed. Okay, I mean, that much space. So just understand, my whole life has to kind of fit in this very small space. I mean, my working life. And, it's just doing experiments just isn't practical. Anyway, but I'll try to get to some of them I have to. I'll just say the Aero Soap Breeze guy, I emailed you. Could you reply? Just one way or the other, just so I know I'm stuck with this. Because it just seems like I'm just going to have to spend so much more time than somebody else would have to do these simple experiments. They're going to take me 10 times more time than it would take somebody else who has the stuff and sitting right there. So anyway, it's just irritating. But anyway, there's a lot of things irritating. Just every day it's just irritations. But you already know that probably, unless you're one of these silly, life-loving, whatever, angel people. Anyway, it's all for the best. We're gloriously going to the glorious gloriousness of the glorious of the glorious. Anyway, the grand human accomplishment. Sorry, it's just all so frickin' ridiculous. Anyway, in the context of the real world and how it's devolving right before our eyes, it's devolving. You can see it. Well, you can see it anyway. You see it a lot more. I didn't live where there were a lot of people before. Now I do, and you can just, the devolution is so obvious. But anyway, on to the subjects. So I really am. I find this very curious that nobody's really interested in these questions. So I can ask so many times, why haven't they repeated the editing experiment? And there's just no. All these people defending science, loving science, loving physics, like Professor Lewin, but they don't love evidence. They don't love experiments, and they don't. Why don't they love those things? Because that's really what physics is. That's what understanding is poking things, testing things, seeing what it does. And they don't have much evidence. They don't have much will to do that. And that's sort of like religious people. Religious people are the things that don't want to poke the truth. They don't want to poke their Bible and figure out who wrote it and where it come from, and is it really the Word of God? Did God really write it all? Are all of the characters who made a contribution pristine? Are any of them molesters or some other bullshit? Where are they getting their truth from? They don't really want to know the source, but scientists really, I think, should. People interested in the truth. They want, poke it, kick it, knock it down, do whatever you have to do, dissect it. Yes, it's ugly and disgusting, but yes, let's do it. Let's find out how it works. But it just doesn't seem like there's, so among the critics, of this channel, it doesn't seem like they have much will to do any of that. Anyway, I pondered a couple of obvious questions. Now, I've pointed out that fundamental underlying all this is some theory of what energy is. And I can show you websites that'll give you conversion charts for joule. You can convert it into watts and all kinds of horsepower and all kinds of different pieces of energy, types of energy, let's call it. And they even have a thing called a foot pound, which is a pound raised 1 foot. So again, it's this raising thing. And you're arguing, well, why don't they just weigh a joule? I mean, it's obviously, by definition, a joule is a weight falling a distance. And it's what's the impact of falling that distance. So it's the same thing as calculating these two hands hitting each other. It's about a joule. The calculation is the same. It's about weight. It's the weight of the pressure of the two hands hitting each other. You could think of them as, buildings, Empire State Building. I could lift it an inch off the ground, and you could understand if I put a generator under there, it's like having a giant reservoir of water. And, so it's hydroelectric, and I could just, take the energy out of the weight of the Empire State Building. I mean, the hydroelectric is kind of a good example because all you're really doing is taking advantage of the energy built into weight. It's the weight of the water that the whole thing relies on. If the water doesn't weigh anything, then it's of no value. You can't derive any energy. So it's weight that's creating the energy. The joules are in the weight. So this seems like the most elemental, even more clear than turning it into a watt is turning it into a pound. Understanding that you should have just a direct conversion between joule and a pound. How much weight is a joule? How much pressure? And it seems like an obvious thing. And you're saying, okay, so why would a scientific type, somebody who admires, Sean Carroll and Degrassi Tyson and whatever, SpongeBob, the Science Man, all this, popular science. What do you think their response would be? I mean, I'm curious as hell. I mean, what their response would be when you say, well, why haven't you created an equivalence between the most fundamental form of energy there is, weight? I mean, weight's the most fundamental form of energy. You can't get any more elemental. That's the hydroelectric thing. It's so elemental. You're just taking advantage of the fact that water is heavy. Yeah. And if you lift it, it's a high distance, then you get lots of time to extract energy from its weight, as gravity produces it. Obviously, the force you're taking advantage of is gravity, but clearly you're doing it through this simple mechanism of creating momentum, weight. So, I mean, I could go all the way back to, explanations about fish and different things. I don't know why I'm on this particular screen. It doesn't help you very much. There's nothing going on, physics-wise. You just can't find a meaningful physics video, among my subscriptions anyway. So, I'm just soliciting this conversation. So somebody who has some answer, why haven't they repeated the Eddington experiment when there's 400 times better resolution from space? I mean, come on, you can come up with a good answer for that. And why there isn't this, why physics doesn't go to the simplest form of understanding what energy is, which is weight, pressure. That's the essence of energy, is something is going to apply a pressure to something else, and that's going to be your energy, and you could just quantify it into this unit, and it should be quantified into the unit. So then we could just say how much weight is how many watts, because the fact is it is a certain amount of watts. All right, so I guess I can illustrate something here. Attempt to combine. It's kind of combining more than one subject. And understanding what weight is just understanding that you're taking a mass and you're giving it velocity, and velocity is essentially just a way of taking something that's in chaos, right? So you could say something has, stuff in it, and its stuff is going in all kinds of directions. And what you're doing when you're creating weight is that you're organizing it, essentially, in the sense that you don't have the scatter. So you could think of it as, this would be its maximum speed, is that every available bit of movement inside of it, okay, you convert all of those movements into just this kind of movement. So you just have this kind of movement inside of something, and you say, well, it's going as fast as the movement inside of it, and this would be, in my opinion, the speed of light. Because the stuff moving inside of you is all just electrons and protons, and those electrons and protons are just moved by the actual force and directions. So they are complete slaves to the field around them. An electron doesn't do anything on its own. It only does what the field is doing to it. So depending on what field it's in, that is what environment, which way it's raining, which way the wind is blowing, these are all, I think, perfectly appropriate ways of understanding that the field of energy is creating a wind. When you shoot a laser, you're blowing a wind in a very tight beam at something. That's essentially all it is. It's just to wind. Or I can compare it to fish. Now, these are analogies, they're not perfect, but they give you some understanding, like a school of fish. This is all the energy it's got, is the fish. So it's got a fish going that way, it's got a fish going that way, a fish going this way, and overall, if you add up the direction of all the fish, and they all have a tendency to, obviously stay within the confines, so they change their direction to stay within the school. But there's lots of motions in the school of fish. But there's a certain number of motions all in one direction. There's a plus. You have more fish doing one thing, then the school moves commensurate to that division. So if there's 10 extra fish, then it moves 10 fish, okay, as a percentage of all of its fish. So it's 10 fish out of, 1,000 fish that are, there are 10 extra fish miles per second in a direction, then that's how fast the school is going to go. Just divide the number of extras over the total number, and that'll tell you how much you're going to be moving the speed of a fish going this way. So if all the fish are going 20 miles an hour, blah, 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 you can just do the calculation, but the school moves based on that mechanic. And a correlation could be written to say that's exactly what matter's doing. So when matter's interacting with matter, it's just exchanging, what it's got with something else in terms of its fish, which way they're going. It can either share it, that is, it can give part of it, and then they can become equalized, or it can give all of it to something else. It can just divide up the fish. Yeah. Okay, eraser is difficult to access, but I will use it because I'm a responsible adult. Wow, see, that didn't work too well. Yeah, it's keeping it, damp and flexible is the problem. So I have to store it in something, and the storage device isn't accessible. Blah blah blah. The logistics of life are just such a pain in the ass. Anyway, all right. So I've used my two analogies, and so I've used before the laser beam. So that there's another analogy, and that what you're really saying is that when the force is so clean, okay, that everything's moving exactly parallel, nice straight lines, and nothing's going in these directions or this direction, nothing's spreading, blah blah blah, minimal anyway. Obviously lasers aren't perfect that way. You're concentrating, the energy, and so that's not the norm. Okay, now the individual force is always a nice little laser beam. It's a nice straight vector, but it's hard to get a bunch of the forces together. That is, take a complex, take a hot thing, where the energy is going in all directions, and somehow reflect all the bits in just the right way to get them all going in the same direction. Okay, so that's the hard part. So velocity isn't something common in the sense that it's not, you have to acquire it. You have to, something, for every little bit of stuff flying through space, something had to launch it. I mean, the Earth's momentum right now going around the sun had to come from something, some events. So each little piece that made the Earth, it had a vector of motion, and all of those have added up over billions of years to add up to where the Earth has a velocity. All of those little influences, and so there's rules about the influences. Like once you're in a solar system or in a sun-dominated system, it becomes more and more probable that the other objects that are going to hit you are going to be compliant with that environment, and therefore going in the same direction as you, and therefore adding to your velocity over time, and blah blah blah. But anyway, don't want to get into all that. So so there's a reason to think that velocity, a high velocity, is a little bit special, but there's no reason to think it should be squared. Okay, there's no logic to think that's a rational thing to do to it. It's just this idea that it's harder. The universe makes high speed less than, it makes low speed objects easier than it can make high speed objects, because just a mere, just a tiny bit of extra in a direction is easy to acquire. cleaning out all of the scatter, all of the noise is hard to do. So it's like any environment. It's hard to make a soundproof room, you know, a perfectly soundproof room and all that kind of stuff. So that's why velocity seems, you know, can seem like it has meaning beyond just being some extra, but it really doesn't. You know, all it really does mean is that you've taken, you know, you've filtered. It's the complex thing. You know, it's you need a very complex environment to cause something to move in one direction, and to have, you know, like I said, to change its material form. That is, all the influences that, like, to eliminate this influence and to eliminate this influence, and to only accept this influence and this influence and this influence. You know, so it takes a very special environment where you've taken out all of the interactions with the rest of the physical reality. You know, you don't let the rest of the reality in. You just let this one kind of reality in to force something to move at a high velocity. So high velocities are difficult to create. Now, if you're in gravity for quite a while, you can understand that that's a very, you know, a dominant environment. So as you're falling, I'll just make an image for falling. As you're falling, okay, you just keep getting hit by energy with this vector, with this vector, with this vector, with this vector. And you're getting hit, obviously, by more energy than you'd be hit in these other vectors. So you have, through the process of falling, you can just understand it as, well, I'm having rain hitting me a lot this way, and very little rain hits me this way. So each step I take through here, I'm getting changed more this way than I'm getting changed this way or this way. You know, all the other side directions are, if I total up all the other influences, they're less than the total of the rain coming this one way. So as I fall, I just keep getting more unclean. My matter gets less and less noisy. The dominant signal, you know, is changing my disposition, my internal structure, because it's hitting the fish going this way and say, go that way. And it's hitting a fish going this way and say, go that way. And so it keeps converting all the noise elements inside the structure of my matter, all the bits of the matter that are doing the wrong thing in terms of not going in the direction, and converting them into going in this direction. So you're just, it's almost like the Christians taking over, and you know, the Crusades, they just kill all of the other noise. So the only noise is Christianity, you know. Really a stretch of an analogy. But, yeah, so the idea is that you're just measuring the weight of something. You know, velocity is weight. It just makes you have a weight in a direction. So the more velocity you have, the more, you know, of a bias of velocity. So when you're in gravity, right, you're just sitting here minding your own business, and let's say you're neutral, okay? You have the same stuff going in all these directions. Gravity acts on you, and it's obviously converts you, okay, into having a little bit more going this way. And the longer you're in the gravity, this is falling in the gravity, the more that conversion takes place. Now, the only thing that stops the conversion from taking place with you gaining more and more velocity, is the fact that you hit the ground. The ground is doing the same, is opposing. Okay, you push in, you find a pressure zone that is the same as the gravity zone. So you'll fall into the other matter, you'll dent it exactly to the point where this, the 9.8 meters, equals this, 9.8 meters. And when those two are equal is when you stop moving. So you sit here. But you can tell you're still imposing. It's a fight, a constant battle between this pressure and this pressure. They're constantly pushing at each other. And that's why you can feel it, okay, pushing against you. You can feel it happening. It's because it's a constant. It's still happening. You're still moving, essentially. The weight is still pushing on the ground, the spring of the ground. So you're really constantly jiggling on top of that spring, okay, which is the stopping force of the ground. The ground's inability to have all of its billions and billions and trillions and gazillions of material bits to join your school. They don't want to join, so they're resisting, hitting you back this way. They're hitting you with fish, the opposite direction. But this is energy right here. This compression of the spring, essentially, is energy. And like I said, that should be defined as a weight. And we just weigh things, and we can say how much they weigh will tell us what their energy potential is. So when a thing hits another thing, when a bullet hits something, it's actually imposing a weight. And it's a weight per unit of space. So it's a pounds per square inch. It's imposing pounds per square inch on a surface, and obviously if it's got enough pounds per square inch, it's heavy enough, it'll keep going. Just as if I make something heavy enough on the earth, it'll plow through it. It has to be very heavy, obviously. But velocity is weight. So it's velocity that makes you weigh something on earth. It's a velocity that makes you compress the spring. It's momentum. You know, in simple terms, momentum is really important. It's a really important idea. And so it's just a matter of calculating how much weight, how many pounds per square inch it hits the surface with, and that'll tell you exactly how many joules of energy, you know, equals pounds. You know, gotta have there's probably a symbol for pounds, right? There should be an arrow going this way. Anyway, yeah, so that's the, what's irrational about this analysis? See, that's the, you know, Blockberry, you can send me an email with your explanation. I mean, why is weight not relevant? Not relevant enough for them ever to have established the simple experiment is how much does a Newton weigh when it falls 1 meter? Why is it, you know, that's the definition of a joule, essentially. It's the exact definition, actually. The definition of a joule of energy is 100 grams, or something close to that, falling 1 meter. Okay? That weight is a joule. That's by definition. And they've never done that. There's no evidence that anybody ever did this experiment. Just drop 100 grams, measure. See, take the spring's compression, okay, when it compresses because you put 100 grams on it, okay? So now you know how much 100 grams weighs. And I guess I should make that bigger. All right, so you know how much deflection in the spring there is. So let's just say there's that much deflection in the spring. Okay, take that off now, and then just drop a stick of butter, 1 meter, and the spring will deflect, a maximum deflection. And that maximum deflection will be a certain number of newtons, okay, and that will be a joule. So you'll have a direct conversion between newtons and joules. You'll know exactly, you know, in every circumstance, you'll be able to just say, well, what's the energy? I want to know how much energy it is. You'll know how much energy it is. Because all the energy is in the form of mass that's applying a pressure because you gave it motion. Motion is energy, and mass and velocity are the elemental things, the constituent bits that make, you know, mass and velocity. Okay, they're all the ingredients. It has to be a piece of matter, it has to be a fish, give it a velocity, and you've now created a piece of energy. And then if you're going to measure the energy of an object, it's really the only part we call energy. That's a little bit too low. The only thing we call energy is the part where, so if I have an object and it's doing this, you know, it's doing every direction and therefore going no direction, I say it doesn't have any energy. Now it obviously has lots of energy in it, it has lots of movement and stuff, but it doesn't have what we call energy because it can't interact with anything. It's not going to have a trajectory that will crash into something, and it's not going to apply its weight anywhere. So the stick of butter has a weight in space, in the sense that it has energy, it has capacity. But until I give it motion, okay, until I give it a bias in a direction, until I convert it into something that has more in one direction, that's what we call energy. Okay, so energy is a difference. Energy, we're cheating the word energy because we're not accounting for the fact that it's all energy. And the only part we're calling energy is when there's a decided bias in the energy. You know, when more is coming from one side than the other side. When there's an imbalance in the energy, we call it energy. So we only notice it when it's imbalanced. We don't notice it when it's in balance. And pretend it doesn't exist in some way. I don't think most of us do that, but I just mean that's what the physics is essentially doing. Alright, so yeah, maybe I'll pause here. Maybe I just make a short video. Try to pause here. And I'll think if there's anything else I need to add. Alright, did think of something, so we'll go back to the board. Yeah, I wanted to talk about, so there's a place in a Professor Lewin video where he's explaining that if something already has a velocity of say 500 miles an hour, and I apply a force, okay, the same force I'm going to apply to something going 50 miles an hour, alright, exactly the same force, the same amount of fuel I'm going to burn, and so it's a rocket engine, let's say, that's the analogy used. When I apply it to the thing going 50 miles an hour, I'm only going to increase the power of the object, you know, the energy of the object, okay? I'll only affect it by, let's say, 1,000 joules. That's all I'll add to it. And the same fuel, when applied to something going much faster, will create, 100,000 joules of an increase. So I'll gain 100,000 joules of extra energy from the same exact force as I did here, you know, and that's an implication of 1/2 mv squared. So that's what it does. Is that it means that in gravity, okay, the same thing is true. If I'm moving fast in the gravity, you know, if I have a fast velocity, when the 9.8 meters per second, the rain, the little specific amount of extra rain I'm collecting, the extra amount of energy I'm pulling out of the gravitational field, somehow the same amount, you know, depending on how fast I'm going already, the same gravity in will create huge differences again in, you know, differences like 10,000 to 1, okay, in terms of the increase in my how much energy I have. So the amount of extra energy I get from gravity is completely dependent on how fast I'm moving in it already. If I'm moving faster, I'll get more than if I'm moving slower. Somehow the gravity pushes more. Now, intuitive, we have, you know, not intuitive, but even by propaganda, we have this opposite impression that it gets harder and harder to push something, to give something energy as it's going faster. But the kinetic energy theorem says exactly the opposite, that the same force will give much more energy to the object applied to something that already has velocity. The same fuel will somehow create more joules of energy. It's just a fact. And that doesn't make any sense, right? That the same amount of fuel, the same explosion, okay? So we'll call fuel an explosion. So we have the same exact explosion, and we apply it to an object already moving, and we apply it to an object standing still. And somehow that same explosion will convert into many more joules here, you know, 10x, 100x times, 100 times more energy here than here. You know, does that really make sense to you, that that could be true? That somehow the, you know, you really disagree completely with the wind or the rain analogy. You really don't think that these forces are actual forces. You don't think anything actually is a force in the sense that the force isn't made of some quanta, you know, quantizable bits of energy. that are creating an impact on something, a pressure, and pushing it in a direction. You really don't think any of that's the physical reality. And somehow you think the force is just some magical little sparkly thing, and the magical sparkly thing can be 10,000, or it can be 1,000, or it can be 100, or it can be anything. The sparkly thing is a sparkly thing, and you know, it's like some kind of video game where the Pac-Man can eat the same exact thing, you know, and if it's moving, the same exact thing is, you know, got 500 calories, and if it's not moving, you know, if the Pac-Man's moving slow, it only got 1 calorie. You know, is that it? You think physical reality works like that? I don't know. So there's another little added bit. That part really just doesn't make any sense, especially when you apply it to gravity. You got to know that gravity can't impose more energy on something. You know, because why would it care? And the very idea that it's moving in the same direction as the gravity, you would almost think that, well, gravity would be less effective because it's moving the same direction as the gravity's pushing, so the push would be less effective. And it's supposed to be exactly the opposite. That somehow the pushing gets more effective the faster the thing's going. I mean, I think you obviously know that if you want your pushing to have the most effect, you don't move the thing. You know, you push something stationary or something really moving very, very slowly, you know, just to get over the initial friction. And that's the where you're going to get the maximum amount of conversion of your work into pushing. And the faster you have to go to push, the more inefficient you get at pushing, because now you're starting to not be able to grip the road with your feet, and lots of things start to break down in terms of you converting your energy into an effective push. And they're saying it's exactly the opposite, that somehow it's so much easier to push something moving and get much more energy into it than it is to push something moving slower, you know, fast things. Yeah, so that's another argument and such. So I'll pause again, see if there's anything else. Alright, so I guess I'll just summarize the simple experiments that need to be done and that I would prefer not to do still. So anyway, so just all you need is a spring, kind of a good spring, a spring that's kind of loose, okay? And you'll just put a stick of butter on the spring, okay? You have to design a little platform for the weighing, and you put a stick of butter on it, and you see how much the spring stretches, and you'll see how much the difference is. Well, the difference will be down here. So you just measure how far the spring compresses with a stick of butter, and then you just lift the stick of butter a meter high, and then drop it onto the scale, and you just video whatever the deflection of the scale so you can see what the maximum amount is, and let's assume it'll be somewhere down here. I'm predicting it's going to be 2.3. I think that's the number. So in the 100 grams we'll end up weighing 230 grams. Should be right. There's just a vague guess. And that would be a joule. So a joule would be the weight of 230 grams. It seems like it should be more than that, actually, so this number might not be right. But anyway, so that's all you got to do there. You just see how many units of butter weight, okay, a stick of butter, how many extra units you get when you drop it a meter. And that'll just tell you what it weighs. So that's so simple. Somebody else got to be able to do that experiment. All right. And the other one is, you know, just this spring thing. You know, just take a spring, compress the spring a specific amount, put a, you know, a 2-mass object on it, and measure its velocity, and then put a 1 mass on the same spring, same compression, put a 1-mass object on it, and measure its velocity. Alright, so we can know whether their theory that the lighter thing can only go 0.4 faster. Okay, can only go 0.4 faster. It only, whatever this velocity is, it'll only be a 0.4 increase for this one. So it's really, really lame. You know, the lighter thing doesn't go 1/2 the velocity. You know, it only increases the velocity by 0.4. So that's their theory of what it means, this kinetic energy theorem. And I say, yeah, that's got to be wrong. So the trick is this, you know, do different springs, because if it's a weak spring, it won't be able to produce the velocity. So the stiffer the spring, the faster the velocity it can produce. And so you have to have a spring stiff enough to be able to get up to the faster speed. For, why did I put a half here? The faster, this is the 2x speed. Okay, this is the 1x velocity. To get up to this faster speed, this has to be a stiff enough spring. Or you have to compress it the right amount, you know, not too much. If you compress it all the way, that'll screw up the results potentially. Okay, if it's, you know, because you've, well, I don't want to go into it. You can sort of understand that if you compress the spring all the way, you've minimized its variability in terms of what it can do. And so if you compress it halfway, then you're less likely to create a messy result. You're more likely to get, it'll be a better experiment, let's just put it that way. Too hard to explain why, but yes, it's a better experiment if you don't push the tolerances of the spring. Stay within its tolerances. All right. So that's it. I mean, they're dirt simple experiments. The fact is, nowhere is it done on the internet. So there's not anywhere on the internet I can find, or other people searching for me can find, where they measure the weight of a stick of butter falling a meter, which is a joule, something they've had for 100 years, this unit, and they've never done the simplest experiment to find what a joule is, because a joule is a weight. And this simple experiment, never done. There's no video of somebody doing this experiment, even though it's so simple. And so, in a way, your video is going to be very popular and famous, because everybody will be able to point to it and say, well, here's the proof of the kinetic energy theory, see, because it does this 1.4 thing, you know. And obviously, you know, if you do the experiment badly, you can prove it. But I just mean, if you do the experiment well, with, you know, understanding the variables, the stiffness of springs and all that kind of stuff, you know, it'll give us a ground to work from. See, there's nothing grounding this conversation, because it's perfectly legal for them to think this is true. And as long as it's legal for them to think this is true, you can't have any conversation about paradoxes and all this other stuff, because there's something that's, you know, you can change the elemental rules. The elemental functions can be changed. So until you have the same, until you agree on some vocabulary, right? I mean, this just breaks all vocabulary in the sense that you can't even talk about concepts at all until you establish these basic definitions. I mean, and so something this fundamental, there's just no experiment, no Faraday experiment. Nobody in the history of science has done this simple experiment. I mean, it's just, I'm sorry, it's almost, what? How is that possible? It doesn't seem possible. It doesn't. If somebody gave me that, it's, you know, before I did all of this work, if somebody told me there's no video on the internet of, you know, just compressed, you're using a spring and shooting a light object and a heavy object, you know, I'd say, no, there's got to be one. Now, there sort of is one, I would argue. The Professor Lewin experiment with the carts really is this experiment, okay? And the velocity really is, you know, half or twice as much, however you want to look at it. And there is no 1.4. But anyway, that's where we are. So we'll just move along. So, I mean, I just have to, like I said, I have to be convinced that there's just nobody better able to do these experiments, and I actually have to do them. I have to actually waste so much time doing these simple, stupid experiments, and just, it displeases me to waste my time. But apparently I'm going to have to. So far, it looks like. Because nobody's volunteering, and shit, that sucks. So anyway. So, till the next time and such. I guess I'll do this thing. I have to reorganize everything. Alright. And so this has been a DraftScience video presentation. And such. Yeah, that's all you can say. I can't say anything nice. It's just there's, who am I talking to? You'd love to know this kind of stuff. Who's really listening to these videos? I mean, we know, like, YouTube has really confined the audience for videos. Like, it only recommends, the popular things, this, that, and the other. It's not really on the radar anywhere. It doesn't really have an opportunity to be, for somebody to even have the choice of knowing it exists, kind of thing. The internet is just the Google net. There is no internet. You can't access the internet. It's just the little piece Google will show you. Whatever's on that first page of search results, whatever's on the, the top of those recommended video list, that's all the internet there is. And it doesn't even let you do decent keyword searches, frankly. But anyway, we're just stuck with what it is, so it is what it is. Anyway, nobody does any searches either, so. Alright, anyway. Enough commentary. So, again, this has been a DraftScience video presentation. Thank you for your attention, I guess. Thank you for watching the video, I guess. I don't know. I mean, there's no point in thanking the people who are just trolls, who are just, have nothing to say about the actual subject, except they don't like me. How very interesting. Not. I mean, I should make my list of all the people I don't like. Jesus Christ. I should waste my time pointing it out in videos. There's no point. I should waste my life, really, just going on about all the people I don't like. Not a good idea. So anyway, till the next time and such.